Exploring the Solar System Part 4, Exoplanets, planets around other stars. So I'll ask the question, why do we bother looking for exoplanets? How do we go about finding them? How do we look for life elsewhere in the universe? And again, what is the next step, as it were? So we can ask, we live in a solar system which we've known about for hundreds of years, but is our solar system typical? What is going on around other stars in our galaxy? We can't really talk about what's going on beyond our galaxy at the moment, but we can ask whether our solar system is typical. Are there other planets like the Earth? This is a question we've been asking for an awful long time. If there are planets like the Earth, then presumably life could easily exist on other planets. It might be possible for life to exist even without other Earths, but that's perhaps the most sensible place to look first. Is there life elsewhere? If we can get an idea of how many exoplanets are out there, we can get an idea of whether or not life is likely in the galaxy. And hopefully studying other solar systems will also help us understand our own a little better. So, planets orbiting other stars, we can find them, we can detect them by various methods. There's 5 methods, of which I'm going to talk about 3. Radial velocity method looks for the fact that stars wobble because as a planet goes around the star, it tugs on the star, and depending on the mass of the planet, it can make the star wobble as the planet orbits. And that we can see by looking at the spectrum of the star. So that's called the radial velocity method, and we're looking for stars that wobble. Second method is transit, whereby a planet might move in front of a star. So we're looking for effectively the shadow of the planet. We're looking for the light output of the star dropping because a planet is casting a shadow in front of the star. Third method is, in principle, we can look directly and try and image a planet around another star. That's rather tricky because stars are really bright. They can be perhaps 1,000,000 times brighter than a planet, and therefore trying to see a very faint planet right next door to a very bright star is a very difficult technical problem. But there are ways around that. And the 2 other methods, which haven't found that many stars yet, and I'm not going to talk about them in detail, but they are discussed in the handout that I'm going to make available to you. One is called microlensing, that bends light as a distant object passes close to a star with a planet. That can bend the light in a characteristic way which we can recognize. And finally, there's the technique called astrometry, which means effectively mapping out the positions of stars very accurately in the night sky and looking for any of them that appear to be moving in a way that's consistent with planets going around those stars. So let's look at method number 1, radial velocity. If we imagine a star with a planet going around it, this cartoon is exaggerated for the sake of clarity. If a large planet goes around the star, then they both orbit around their common center of gravity, which means the star sometimes is coming towards us and sometimes is moving away from us. And so the light from that star will be so-called red-shifted or blue-shifted. The light will be shifted towards the red end of the spectrum or the blue end of the spectrum, in much the same way that if you hear the siren of an ambulance, as it moves towards you and moves away from you, it seems to change pitch or frequency. It's the same idea, the so-called Doppler shift. Here's a slightly more accurate representation compared to the previous cartoon. If we imagine a planet going around a sun, as indicated on the left, as seen from above and as seen from the side, then the speed of the star towards us varies according to that sine wave that we can see in the top right-hand panel. And that changes the spectrum from the star as indicated in the bottom right. Any features that we see in the spectrum of the star get shifted a little towards the blue or a little towards the red as the star comes towards us or moves away from us. And spectroscopy, taking the light from the star, breaking it down into its colours and looking at the spectrum, That is a very precise technique that allows us to see even tiny changes to the motion of a star, from which we can infer the presence of a planet. Method number 2 is looking for a situation when a planet moves in front of the star. That only occurs when we're seeing a solar system edge on. But if a planet moves in front of a star, then the output of the star, the light output, the brightness of the star dips, according to the little cartoon you can see on the bottom left-hand side. If we were to monitor the brightness of the star, it's effectively steady unless a planet moves in front of it, in which case the light dips. Planets tend to be a lot smaller than stars, so the dip isn't much. The dip might only be perhaps 1% of the output of the star. But as long as we measure the output of the star accurately, we can see these dips, which we interpret as being the passage of a planet in front of the star. If we have a big planet and a small planet, as seen by these two cartoons, a big planet will block more light, and so the dip will be deeper, as we see on the left-hand side, compared to the smaller dip on the right-hand side. So by measuring by how much the light dips as the planet moves in front of the star, we can get a measure of how big the planet is. How big in terms of its size, not in terms of its mass. The wobble that we saw in method 1 will depend on how massive the planet is, but this method gives us size. It would be great if we can use both methods on the same planet, because as we would then be able to measure its mass and measure its size. And I'll come back to that point in just a moment. If a star happens to have more than one planet, as indicated by this cartoon, then if we look at the light from the star in the left-hand side, we see it dips when one planet goes in front, and then that's finished its transit. But then we find two other planets, there's a dip, and then another dip from the third planet. So you can see the light output from the star is more complex, but we can figure out how many planets must produce this particular change of light level from a star. Even if there are half a dozen or more planets, and if we have enough data, we can figure out what that solar system looks like. So although ideally the light would do that indicated by the white line, what we actually have is a whole load of data points measuring the brightness at different times, and then we try and fit that data to the white line to determine what are the characteristics of this particular planet that is transiting the disk. Let's have a look at some actual data. So this is data from the James Webb Space Telescope of a particular planetary system that goes by the weird name of WASP-96. And here, this is the actual measured output of the star. And the scale here, if you can't read it, is 100% where it's level, and it drops to about 98.5%. So this particular planet is blocking about 1.5% of the starlight. And so we measure the background, and then we see the dip, and then the planet finishes its transit and it goes back to where it was. And from data like that, we can deduce the size of the planet that's moved in front of the star. And depending on how often that happens, we can work out what the period of the planet is. The third method is so-called direct imaging. Let me just go back to the start of that. If we have a very bright star, we can place a disk in front of the star and block out the starlight to reveal the much fainter planet that was sitting right next to it. If we allow the starlight into the telescope, there's so much light there, including a whole load of scattered light represented by this blurry disk there, that it's very difficult to see the planet. But it is possible to block out that central bright star using a so-called occulting disk. And here is a time lapse. Let me play that video once again. We're blocking out the star in the middle and seeing four faint blobs in this time lapse taken over a few years, and it's fairly clear that that inner blob is moving quite quickly and the ones further out are moving more slowly. Just as we would expect when we look at our solar system, Mercury goes around the sun quite quickly, Earth takes a year, Jupiter takes 10 years, Saturn takes 30 years, etc. The further you are out in the solar system, the slower you are moving. And that's precisely what we're seeing here. Fortuitously, we happen to be seeing this solar system from above, and so we're getting a bird's eye view of the way the planets are moving. In this particular case, it looks like we have 4 bright planets. There might be a few fainter ones in there, but so far we've imaged 4 of them. It also works if we are edge on. So here we've blocked out the light from the star, and when the planet appears from either side of the occulting disk, then it's possible to see the planet. Again, let's run that video again. When the planet appears, we can see it poking out there, and then it's going round the star, behind the star, and then appearing on the other side again. Again, a time lapse taken over many years. So we have a number of different techniques that allow us to get various properties of the planets. And we've already seen that radial velocity, how much the star wobbles, that effectively tells us how massive the planet is. The transit blocks a certain amount of light depending on the size of the planet. And also, if we break the light from the planet down into its spectrum and use spectroscopy, we can get information about what the atmosphere is made of. So if we can apply all of these techniques to a particular planetary system, then with the mass and the size of a planet, we have an estimate of its density. And we can guess it's the type of planet, because if it's a very high density, it's probably a rocky planet like the Earth. If it's a very low density, it's more likely to be a gas giant or something like that. If we factor that in with the fact that we can estimate the temperature, if we know the period of the planet, then we can estimate how far it is from its host star, and the spectrum of the star tells us whether it's a hot star or a cold star. Is it a few thousand degrees surface temperature, or is it tens of thousands of degrees surface temperature? If we know how far the planet is from the star and we know how hot the surface of the star is, we can estimate the temperature of the planet. And so we can tell whether it's more likely to be an ice planet or a water planet or a lava planet, depending on the temperature and the type. So by combining all of these bits of information, we can start to build up properties of all the exoplanets that we can see. And this is a very small selection of them. This exoplanet zoo shows us a few hundred or maybe 1,000 exoplanets. We've actually determined the properties of about 6,000 exoplanets so far. These are all plotted. There's no particular rhyme or reason to the position other than any planet that's relatively cold is on the left and any planet that's rather hot is on the right. So on the extreme left, there's a surface temperature of the planet of something like -200 Celsius, very chilly. And in the position shown marked there, the surface temperature might be as high as +200 Celsius. Just to give us an idea of scale, some of the solar system planets are shown in this diagram. If we blow up that rectangle, we find there's the familiar Jupiter and Saturn and Uranus and Neptune, just to give you an idea. So you can see that Jupiter is a relatively large planet compared to all of the planets we've seen so far. But if we were interested in whether or not any of these planets could in principle have liquid water rather than simply water vapor or solid water ice, is there a possibility that some of these planets have got liquid water, because we think that's a good possibility for starting life? Well, we have to look in the so-called habitable zone. When we think about how far they are from their host star, many planets will be too cold for liquid water to exist, and many planets will be too warm for liquid water to exist. So there's only a relatively small so-called habitable zone, the Goldilocks zone, that's not too cold or too hot, but the ideal place for liquid water. So if we think about the planets in our solar system, Mars is too cold for water, there's only ice there. Venus is too hot, Any water that existed would be vaporized due to its surface temperature, and no surprise, Earth is in the habitable zone. Earth is there in the so-called Goldilocks zone, not too hot, not too cold. If we have a think about some of these candidates, what have we found out about some of these candidate planets? Well, some of these planets are really close to us. Proxima b, which is in part of the Alpha Centauri system, the closest star other than our Sun, it's only 4 light years away, and yet that system has a planetary system. If planetary systems weren't very common, what are the chances that there's one right next door to us, only 4 light years away? Discovering the fact that Alpha Centauri has planets indicates that planetary systems are probably a lot more common than we first thought. One of the oldest planetary systems we found is this one, nicknamed Methuselah, which appears to be orbiting a star that's 12.7 billion years old. Now, we don't think there's any way that planets can form after their host star. We think that planets are always born at the same time as the star that they are orbiting. So if the star is 12.7 billion years old, then the planet is 12.7 billion years old. Remember, the Earth is only some 4.5 billion years old, because that's the age of our Sun. So it looks like planets existed very early on in the universe. This is in the first billion years of the universe's existence. Stars came into existence and planets were there right from the off. So it's not something that's only happened relatively recently. In the top right, if we think of the right-hand end, remember that's the hot end of this diagram, some planets have got ridiculous surface temperatures. We can't really imagine life ever evolving on a planet with a surface temperature measured in thousands of degrees. And in the bottom right there, again, this planet is very close to its host star. And no, it doesn't look egg-shaped because that's a mistake. We think that planet is definitely egg-shaped because it's so close to its host star, it's getting distorted by the gravity of the star into a sort of rugby ball or slightly egg-shaped structure. That's based on simply knowing its distance and having some idea of its composition. There were some other notable planets in this exoplanet zoo. One of the largest that we can see on this diagram is this one that goes by the ridiculous name of HAT P67b. Again, they really need to get their naming convention sorted out. This particular planet appears to be something like 10 times the size of Jupiter, but also appears to be less massive than Jupiter, which means its density must be really low. It's been estimated that this planet would have a density similar to marshmallow or something like that. Certainly much, much different from rocky planets such as Earth, and even much different from our own Jupiter. And if HAT P67b is a rather bad name, well, I think the prize for the best name they've come up with so far must be Coconuts 2b. Fantastic. Coconuts, an acronym, Cool Companions on Ultra-Wide Orbits. I think they came up with coconuts first, and then they tried to reverse engineer a nice acronym that means coconuts. Cool Companions means we're talking about planets that are by no means warm. They are so far from their star on ultra-wide orbits that they will be extremely cold. This particular planet is 7,500 AU. An astronomical unit, 1 AU, is the distance from the Earth to the Sun. So the distance of this planet from its star is 7,500 times the distance from the Earth to the Sun. And instead of going round its star 1 year, as the Earth does, it will go round its host star in about 1 million years. So a very, very different situation compared to a small rocky planet like Earth going round the Sun. But in terms of weird, I think, again, the prize has to be taken by this one. Let's not worry about the name LHS 1140. It's sometimes called an eyeball planet because what we think it might look like, and we don't of course know, but we think it might look like that, an eyeball, because its temperature would indicate that it's probably covered in ice. And yet it's close enough to its host star to be locked, tidally locked, so the same face of the planet always points towards the star. Of course, that's not what we have with Earth. Earth turns once every 24 hours, and so everybody on Earth gets a share of the sunshine every once in a while. But this planet, it is thought that one face always faces the star and the other face always faces away from the star. So even though it's an icy planet, probably covered in ice, it is thought that the face that's always closest to the star might get warm enough that the ice melts. And hence it's an ice planet, but maybe with an ocean on the side that faces the star. So it's hypothetical, it's only a possibility, and it's only an artist's impression of what we think this particular ocean surrounded by ice might look like. But the idea that there are some planets out there looking like eyeballs is just an interesting bit of fantasy. So there are a number of spacecraft or space telescopes if you prefer, that are capable of finding exoplanets. Gaia is a European Space Agency spacecraft which has been operating for more than a decade now. Its job isn't to find exoplanets, its job is to map as accurately as possible the positions of stars in the sky. But because it's doing such a fantastic job of mapping their positions, it's actually noticing that some stars are wobbling, indicating that they have planets orbiting around them. So Gaia has found some exoplanets. James Webb Space Telescope is not designed to find planets. It's far too valuable to look at either distant galaxies or planet formation or stars that are being born, but it is occasionally tasked with the job of go see whether or not a planetary system is starting to develop around a young star. So it is looking at planets, but it's not finding them. But there are a number of telescopes that are designed to find planets as well as to study them in more detail. Kepler, back in 2009 in the top left, has found thousands of exoplanets by looking for transits, looking for the dip in light to see whether or not planets exist. And in the top right, there's another ESA mission that will be launched soon called Plato, and centre bottom there is the Nancy Grace Roman Space Telescope, due for launch in 2027, assuming that a certain president doesn't decide to cancel the mission. There's also, way into the future, other plans for the so-called Habitable Worlds Observatory, the HWO, looking specifically for Earth-like planets rather than whatever planets are out there. Interestingly, the Nancy Grace Roman mission, although it will start by simply looking for exoplanets by blocking the light from a star using an occulting disk in the telescope, it's also thought that it might try a different way of blocking out the light from a distant star, not letting the light into the telescope in the first place. And they'll do that, the plans are, by sending up a star shade with the telescope. They will decouple, the star shade will then unfurl and produce a huge 100-meter diameter shade, which will then be flown a large distance away from the telescope, some 50,000 kilometers or so, and it'll be far enough away that it'll be possible to block the light of a star but still reveal the presence of any planets that might be orbiting that star. It'll take a very careful choreography to make sure the star shade and the telescope are lined up accurately with a distant star, but it's thought that that will produce a much higher contrast and be able to see fainter planets. So the star shade isn't yet funded, but there's a possibility of that happening in the future. I mentioned that these telescopes in principle can look for life on other planets. How do we do that? Well, if you think about the idea of a planet going in front of a star, or indeed behind a star. It'll transit if it crosses the front, and it'll get eclipsed if it goes behind a star. And both of those allow us to determine whether or not there's a particular characteristic of those planets that can be determined from the spectrum. Because if we were to look at the light from the star and the planet, even if we can't resolve them, when the planet goes behind the star, we lose the light from the planet. And so if we see a change in the spectrum of the star plus planet, we know that's a consequence of the planet going behind the star. But also, if we think of the planet going in front of the star, if the planet has got an atmosphere, some of that starlight will shine through the atmosphere, indicated by that orange ring here. And if there's any particular molecules in the atmosphere, they could absorb some of the starlight at some wavelengths characteristic of those molecules. So if we look for the dip in starlight at different wavelengths, we might find that at some wavelengths more light is absorbed, indicating that some molecules are absorbing those wavelengths, and we can determine the chemical composition of the atmosphere, which will give us hints as to whether or not there's any life on the planet generating those molecules, for instance, oxygen. So here again is actual data taken by the James Webb Space Telescope. Here's starlight, and here's the starlight dropping due to a transit of the planet. But the different coloured dots here, blown up in the bottom panel, show us that if we look at that dip at different infrared wavelengths, the dip is slightly different. If we look at the red dots, they don't go down quite as far as the yellow dots, and the blue dots are somewhere in between. And those red, blue and yellow dots are taken at different wavelengths, and we choose those wavelengths to give us information about particular molecules. And by doing that for a number of different wavelengths, we can effectively start to see whether there's any characteristic signs of, does water exist in this atmosphere? Does carbon dioxide exist in this atmosphere? Does carbon monoxide exist? And so far, the James Webb Space Telescope has found signs of water and carbon monoxide and carbon dioxide and sulfur dioxide and other molecules, and some elements as well, in the atmospheres of exoplanets. We have not yet seen any spectrum from James Webb that says definitively the chemicals in this atmosphere prove that this planet harbours life. But it is hoped that after enough study we may find some planets that fit that description. I'll finish with this little animation showing how many exoplanets have been found as a function of time, starting in 1992 when the first planets were discovered. On the vertical scale, we're showing a dot whenever a planet is found according to its mass. So here's the mass of the planet in Jupiter masses. So there's our solar system Jupiter, just for reference, sitting there at 1. Anything more heavy than Jupiter would be higher, and Earth would be down here, as it's only a fraction of the mass of Jupiter. The horizontal scale is the orbital period in days. And again, the solar system planets are shown just for reference. So there's Earth being very much lower mass than Jupiter, going round our Sun in 365 days. And there are the ice giants Uranus and Neptune. So dots will appear in this diagram as we go from 1992 onwards. So let's have a look. Let's start going. There's the mid-1990s, not much. A few were discovered in the late 1990s. But in about 2009, when the Kepler spacecraft started looking for transits, the number of planets that were discovered started going up substantially, the purple dots on the left-hand side there. There were other techniques, as you see on the right-hand side legend, and by 2024, we've found thousands upon thousands of planets. But you might look at that and say, well, none of them seem to be where our planets are. Our planets appear to be here, but most of these extrasolar planets seem to be at, well, closer to their host star, and generally speaking, a lot more massive than, for instance, the Earth. So does that mean all of these solar systems are very different from ours? Does that mean our solar system is weird or exceptional or possibly unique? Well, one thing you have to bear in mind when you're making these observations is there is bias in the observations. We're looking for planets of different mass and different size. It's a lot easier to find a big planet because it produces a bigger wobble of the star if it's more massive. And it's a lot easier to find planets with a large diameter because they block more of the light from their parent star. So it's easier to see big planets and it's easier to see more massive planets. Earth-like planets are tricky because they are small and they are relatively low mass. So just because we don't see many of them doesn't mean they're not there. We have to remember the observational bias, and we can statistically work out that if we see this many Earth-like planets, we can judge how many might be there, working on the assumption that yes, they are rather more difficult to find than, for instance, Jupiter-sized planets. And that's what a lot of scientists are now doing. They're going through the data of the thousands of exoplanets that we've now found, trying to work out how many of them are Jupiter-sized, how many of them are Earth-sized, how many of them seem to be between those two extremes. So if you're interested to know what's out there, NASA have produced a dashboard of information on every exoplanet that exists. You can literally look up every exoplanet, find its size, its mass, how long it takes to go around its host star, what its host star actually looks like as in terms of is it a hot star or a relatively cool star. All of this information is in the archives that I've indicated at the top there. And in terms of the near future, in the next few years, there will be more satellites, more space telescopes launched from the European Space Agency, Plato, and from NASA, the Roman, Nancy Grace Roman Space Telescope. In the next 2 or 3 years, there will be more missions coming online. In another decade or more, there will be more that are planned. And these will be not only discovering more exoplanets, they'll be looking at the properties of the exoplanets that we know of to see whether or not we can find more planets like Earth and whether or not we can find evidence for life beyond our solar system. Thank you very much.